Okay, today we are going to do the introduction to acids and bases, cover acid-base strength, and cover the pH scale. So, there's going to be some things that you have to write down, I believe, that are not on your notes, but we're coming back to acids and bases. All right, so we got to back up and do some definitions, which hopefully is review. First one is Arrhenius. Arrhenius's definition of an acid is something that produces hydrogen ion in solution, whereas a base is hydroxide, and this is our most typical definition, but it's very limited because not everything that acts like an acid and base falls into this. Then we've got Bronsted-Lowry. Bronsted-Lowry is a little bit broader. The acid is the hydrogen donor. The base is the hydrogen acceptor, which is a little bit more general, okay? And we will eventually cover Lewis acids a little bit later in this unit as well. Now, for conjugate acid-base pair, essentially what we have to do, and again, I believe there are some things you have to write down on this slide. This is the general form. Remember, anything that has hydrogen ion is our acid, so that's why we're naming this as the acid. And we've got A here as this generic anion. Okay, so whatever anion we've got. Now what happens is that the acid will react with some base. Now we're just going to use water here because water can act as either. Now what happens, and this is, remember, we've talked about some sources will write these in different ways. There's two ways to look at it. One is that the hydrogen ion attaches to the water to form hydronium, but more importantly, this is what's referred to as the conjugate acid because it's what the base turns into after the reaction has taken place. Okay, and then you also have what's called your conjugate base, which is what the acid turns into after the acid-base chemistry has taken place. So the pairs, this is the acid and this is its conjugate acid. This is the base and this is the acid and its conjugate base. This is the base and its conjugate acid, because what we're going to focus on, again, is the fact that we can force these reactions to go back and forth. So we've got to be able to look at it as either perspective. The acid is going to form its conjugate base. The base is going to form its conjugate acid. So in other words, these are two substances that are connected by the donation and acception, or donating and accepting, of a hydrogen ion, at least when we go with these first two. And what happens is that the reality is really a fight over the hydrogen ion between two bases. Okay, either the anion that was attached to it in the first place, or typically water. Okay, and if the anion has a greater affinity, then the reaction, the equilibrium will lie to the left, meaning it's going to form more of the reactants. And if the water has a greater affinity, then it's going to lie to the right, and it's going to form more of the products. Okay, remember this R up here refers to reactants. If it shifts to the left, if it's going to shift to the right, it's going to have more products. Okay, so you got it, and you have to write these down because I don't believe you don't have these written down. So the first thing we should be able to do is look at an equation, determine the acid and the base, the conjugate acid and the conjugate base. Now the good news is, so long as you figure one out, you usually can then work backwards. All right, so we look at these two, and these two don't really fall into our typical acid-base categories. We've got the ammonium ion and the cyanide ion. But if we come over here for a second, here we have hydrocyanic acid and we have ammonia, which we know, even if we work backwards, ammonia is going to be a base. So here's my conjugate base. Here's my conjugate acid, so then I just can always work backwards. This is going to be my base, because remember, the base is what's going to turn into the conjugate acid, and the ammonium is going to act like an acid, and its conjugate base is the ammonia. Okay, again, even though we look at these, oh my gosh, where do I even start? We'll start with the hydroxide. We know hydroxide is a base, so that's got to be the conjugate base, and then we can work backwards. If this is the conjugate base, this has to be the conjugate acid. Don't ever start with water, because water, we're going to learn, can be what's called amphoteric, or either one. And then we've got the base up here. Okay, so figure out one, can work backwards. Now again, it looks a little bit ugly, but if you look over here, this substance right here has hydrogen out front, so we can identify this as the acid. The phosphate is going to be the base, and then you've got the conjugate base, and you've got the hydrogen phosphate ion, which is going to be the conjugate acid. Okay, so this is when you're just given the reaction, you have to identify what the acids and the base, the acid and base, conjugate acid and base pairs are. Okay, now we also have an acid dissociation constant. We're going to get back into our capital K's. This is an equilibrium expression where the hydrogen ion is removed to form the conjugate base. So this is the generic formula that we have here. okay, the generic formula. And remember, a lot of sources that hydrogen ion will attach itself to the hydronium ion. That's kind of the realistic chemistry that we see. So here's our Ka. Okay, when we write Ka expressions, the same rules apply as they did for Kp and Kc, so you'll notice we do not include water because water is a pure liquid. Okay, so remember the products are over here, so you have hydronium ion times the concentration of the anion over the original acid. It's just a generic form. Here is the, the ball and stick figure where this is your water, here's your acid, then there's your hydrogen ion that's going to go be transferred to the water. Okay? All right, so if you look, I'm going to try to follow along with the sections in the book. I'm fairly certain these page numbers are right, so but go with the example numbers. But it says write the ionization or dissociation reaction between Ka expression for each of the following. So for acetic acid, now you'll notice what happens, we get lazy when we write these. Okay, this is nothing different. If you go all the way back to Chem 1, when we took a compound and we split it into its ions, that's all we're doing. But what we get lazy on is we don't put the water. Okay, we know that if we take something and we add it to water, it's going to dissociate, but the reality is that most of us, and you can put the water, you cannot put the water. You're going to see me do this both ways, but we leave out the water because it's not going to count for the equilibrium expression. Okay, so for the this is for acetic acid, this is its dissociation. Ammonium ion, here is its dissociation. And then hydrated aluminum 3 ion is one of those just ugly, one of the ugly complex ions that we had earlier. Okay, this hydrated aluminum 3, not ugly, but one of those expressions. So for example, let me see on this one if I can write the Ka out to the side here. All right, so for the Ka for acetic acid, remember your Ka expression is simply going to be your hydrogen ion over the acid, well, not over, with the acetate. Oh, can I get this in there? Minus over the concentration of your original acid. Okay, I really hope this beginning one is simple. That's the gut feeling. And then you're just going to follow the same things over here. For the ammonium ion, your Ka would be your hydrogen ion and your ammonia over your ammonium. Now I don't have enough space, but you do the same thing down here with the hydrated aluminum 3 ion. And you can see that on page 656. Okay, now when we talk about the strength, we've mentioned this before. I just haven't defined it. I just kind of lied to you and said, well, hey, this is what the case is. But we've talked about the strength of acids, and we've talked about the fact that it is how strong it dissociates. What I have not told you is that when we talk about how we know what the strength of the dissociation is that it all has to do with equilibrium position. So I know I warned you that chapters 13, 14, and 15 are all the same topic. So for a strong acid, that simply means that the equilibrium position lies far to the right, and almost all of the acid will dissociate, which means they have very large Ka values, because don't forget that the equilibrium expression is simply a reflection of products over reactants. So if everything dissociates, they're going to have a much larger number for here. And this also, if we think about the conjugate base pairs, a very strong acid is going to have a weak conjugate base because it's going to win, okay, for lack of a good explanation. Now, a weak acid is going to be just the opposite. And we've defined a weak acid, anything that's not, and then the list is still the same. The still are strong acids, hydrochloric, our perchlorics, all those that's on that list. Everything falls into a weak acid, but what that means from a definition standpoint is that the equilibrium expression lies far to the left. Almost all of the acid stays as the acid, and they have very small conjugate acid, not conjugate acid, they have very small Ka values because it's just the opposite. If most of it stays as the reactants, then the Ka value is going to be smaller, and they have very strong conjugate bases. So that is going to become really important later on, so you just want to make sure that that's pretty automatic. Okay, this is just a little depiction of what it looks like. This is your strong acid, okay, up here. Here is your weak acid, and I'm kind of overgeneralizing. You're going to see this a little bit later. Very strong acids have very weak conjugate bases. Very weak acids have very strong conjugate bases. And then we've kind of got this middle ground that's going to be a little bit, not trickier, but we're going to talk a little bit more about this later. So we're just focusing on the extremes on those. And again, this is just actually showing you the Ka values. You'll notice that none of the strong acids have Ka values up here, or none of the strong acids are listed, and that's simply because they are so much, we don't even list them because everything almost dissociates. So, and water is a stronger base than the conjugate base of a strong acid. You just got to pay attention to these down here a little bit. These will make more sense when we do our problems. Because water can kind of behave, it kind of falls right smack in the middle. And so we'll see where that comes into play for the strong and weak acids. So if you're asked to determine which is stronger, also look at page 14, or excuse me, exercise 14.2. If you look at which species is a stronger base, you got to go to its conjugates. Okay, hydrofluoric is a weak acid, hydrochloric is strong, so that means that the F- or the fluoride ion is going to be a stronger conjugate base than the chlorine. Determine which species is a stronger acid. Water or ammonium, well, hydroxide is a strong base, ammonium is a weak base. So you have to think about the conjugate acid-base pairs on those. Okay. All right, types of acids, these are just some terms that we should be somewhat familiar with. Mostly diprotic has 2 acid protons. Oxyacids have oxygen in them. Organics typically contain a carboxyl group. And what we call hydrohalic, halic just refers to the halogens. Okay, all of our monatomic ones. All right, water is what, like we said, is amphoteric. This can be either an acid or a base. All right, and autoionization of water is where 2 water molecules will exchange a hydrogen ion. And this is what's called Kw. Okay, so we've now got Kc, Kp, Ka, and Kw, and this is the dissociation constant for water. At 25 degrees, Kw, they're neutral. Okay, and we're going to come back to pH here in just a minute. So at 25 degrees, Kw is 1.0 times 10 to the negative 14th. We're going to use that to our advantage here just in a few minutes. So, okay, so some scenarios. Neutral solution is where hydrogen ion is equal to hydroxide. Acidic solution is where hydrogen ion is greater than hydroxide. Basic solution is where hydrogen ion is less than hydroxide. Now I'm going to skip ahead here for just a second. You guys can go back, look at the examples on 14.3 and 14.4 because I'm going to do a couple more of these, but this backs it up as well. Talks about the pH scale. So just refer back to those to take a look. So the pH scale is much more convenient than using concentrations because the concentrations can be really small and really large. pH is equal to the negative log of the hydrogen ion. Number of decimal places, one of the rules is different here. Decimal places in your log value equals the number of significant figures in the original. So however many number of sig figs are in the original concentration, that's the number of decimal places in your pH value. It's a little bit different. I'll keep reminding you of it as best I can. pH increases as hydrogen ion decreases. That's because of the logarithmic in the math. 14.0 is typically what pH and pOH are equal to, so we can use that to our advantage. And pOH is simply equal to the negative log of the hydroxide ion. Now, we really can use any 3 of these methods to figure out the pH or the pOH, and you'll see how we do that. Doesn't matter to me which one you use so long as you use one effectively. One thing I do need to mention is that occasionally with really strong acids and really strong bases you will get some that are off the charts that are negative or over 14. Don't be thrown, it's possible, they're just really strong scenarios. Again, here's your basic values up here, your acidic values down here. These are things, again, this review.